Good morning. It's Wednesday, 10 a.m. So, it's time for another fireside chat with the experts. And today, I'm happy to introduce my good friend and VP of Engineering, Carlos Valenzuela. And today, Carlos is going to address a topic that is a recurring question we have from our customers, which is void detection and how can X-ray help identifying and of course, as time goes by, mitigating and reducing the amount of voiding on your solder joints. So with that, Carlos, you got the floor.
Oh, thank you, Bill. So the presentation we got today is on, skip one, that define defects on BTC assemblies with X-ray analysis. So BTC is bottom-terminated components. So X-ray is one of the main analysis for this type of components. It's probably the most used analysis for defect detection on bottom-terminated analysis, bottom-terminated components. So here's a quick summary we're going to go over today. If you probably joined another one of these webinars, you're probably familiar with the SMT manufacturing process, where things are introduced or defects are introduced. Little quick intro on X-ray inspection, BTC and the need for X-ray, QFN, BGA LED inspection. All of those are different types of BTCs. BTCs and obstructed views. The difference between 2D, 2.5D, and 3D X-ray inspection, and DFM and DFI, which is designed for manufacturing and designed for inspection, and kind of the difference between those two. So design for inspection. So this is something that nobody really does, right? As engineers, you design something and you expect it to work, and then when it doesn't, you're kind of surprised, right? So you kind of have to prepare for that. You have to design with inspection in mind, and those are a couple of things that we're gonna go over today. And it becomes very troublesome and more expensive to troubleshoot or change or inspect components that are not designed to be inspected or with inspection in mind. So here's a traditional SMT kind of production line. So you have every single step of the process, and every single step can introduce some sort of defects. So defects associated with solder paste. So you can have excess solder, you can solder bridges, and insufficient solder. So basically shorts and opens. Then you go into the component placement. You can have polarity, you can have missing components, you can have misalignment, all sorts of issues that, some of them can be caught on an AOI system, but talking about BTCs, it's going to be easier to catch them on an X-ray system. And on the reflow oven, this is where voiding is introduced. This is where the solder is basically melts and it kind of behaves erratically sometimes. So you can have insufficient solder, you can have excess solder, missing solder balls, or more complex defects on BGAs like hidden pillow and coplanarity and things like that. And then bridging and voiding, which are maybe the easier ones. One of the main things that we want to also introduce is when you have an AXI, usually it's at the last step of your process. An AXI can analyze data, can collect data from other machines, and kind of give you a kind of like an overall process of how your line is doing, depending what sort of defects. Certain defects are happening at certain different processes, so you can go back and fix that process to have a more efficient overall result. Here's how basically an X-ray image is produced. You have the main components, which is the source and the detector, and then you have your sample moving it in and out or closer and farther away from the source, creating magnification. There's a perfect example for like a BGA or some sort of a QFN. You are penetrating the object and we're seeing inside, and inside you can see the balls or a BGA or the voiding on a QFN. Next one. So here we can see a side view of a BGA. So BTC, that essentially is the BGA. We can see the balls and we can see the PCB. So with X-rays, where we're going to be penetrating this three things from a top view, and seeing how the balls are actually attaching to the solder and to the PCB itself. So here you see a top view. So here we got the PCB, we got the BGA, you see the little balls on the left side, and here is an actual X-ray image. So you can see all of these are just black circles. We don't really see any sort of easy defects on this one. We can see very even colors, not a lot of voiding, and no missing balls, which is easy one. Here we have a QFN, and right in the middle, we can see a lot of bond wires, which is good. But right in the middle, we can see a lot of voiding. So that's important because that's where a lot of the heat dissipation is happening. So if there's not enough solder, the QFN could actually run a little hotter or not be able to supply enough current that it's supposed to. And that leads to failed product. Here, another quick view. We have a open pin. So over here we can see we're circle that doesn't have enough solder, so it's not making a connection to that pin. Like I said before, some of these might be caught by some other test equipment like an AOI. So once you see void, our TrueView platform has void analysis tools like this one you can see over here. We can see a lot of voiding on this component, and our tools are actually catching the voids on our void tool, our void detection tool. And on the bottom right, you can see a 3D rendering of it. Sometimes it's easy to kind of picture that on a 3D aspect. You can kind of see that they're the actual holes, even though they're not. There could be holes actually. So this, you can actually generate a report from this data. You can see actual percentages of voiding, so you can start analyzing what's a good threshold for your product. LED is another huge market for X-ray inspection. We actually written a few white papers on how voiding percentage can correlate to failure rates and loss of product. So essentially here we can see the LED at the top, the die attach right in the middle, and we can see a void, which is essentially a hole or an air bubble. There's no connection in that area to the substrate that's at the bottom. And if you don't have enough solder, then the LEDs will fail. And they're probably going to pass all sorts of tests. They're going to turn on, they're going to do all sorts of electrical tests, they're going to be fine. But they could fail before they're supposed to, or before warranty expires. So if every single one fails before warranty expires, you don't have a product. Here's a couple images, examples of what an LED looks like under X-rays. So you can see on the top on A, the picture of the LED. You can see on B is just the X-ray image. C is actually detecting the voids, and D is just the 3D rendering of that pad. Then here's on our TrueView software. You can see an LED on the left side in our pad voiding tool, detecting 28.45. That's a little bit on the high side for an LED. So this would probably be a failed LED. There's a lot of, and you can see on the left side, there's a lot of solder missing around the pad itself. So this one is probably missing some solder plus voiding. And here again, another 3D rendering of it. And you can see on the right side, there's a lot of color mapping. For different operators, different colors are better. And they're able to kind of process that image better. Instead of just the black and white, we can go into any sort of scale. You can use like a rainbow. It uses the whole spectrum of colors instead of just black to white. This is something new that we've been working on. It's basically a live void analysis for LEDs. So as new product goes into the field of view, it automatically gets analyzed with our vision tools. Moving on to a BGA Inspector. BGA Inspector is our proprietary BGA analysis tool. So if you see on the left, on the image on the left, we can see the BGA, and we can see our software automatically select all the voids in the field of view and process them. But what's pretty important in this case is that you can do a lot of reporting. So once you get the data, you can analyze every ball. You can see if it's good or not. But how you document it is also an important process. So if you can see on the right side, there's an inspector inspection report being created. So this can be saved on your server. It can be saved as a PDF, share with your customer, whatever you want to do with it. And this is kind of just reporting the data that you've been acquired. And if you don't do this, then you're just kind of relying on a person to look at it, see if it passed or not, and then moving on. So documenting is a big part of the process. To create better BGA tools, we use what is called dual energy. And because the balls on a BGA tend to be very dark because it's essentially just solder, getting a good image on that will mean that you're overblowing or oversaturating the rest of the image, sort of what you see on the high energy image. And what dual energy allows you to do is to get two images and combine them together. So if you see on the left side, we have a high energy image, and on the right side, we have a low energy image. And our algorithms will combine those two images, giving you what we see on the bottom, which is a dual energy image. And this will allow us to see the voids inside, but to also see the traces that are going to the balls. If you can see if there's some blown traces, if there's some missing traces or something like that, we can troubleshoot not just the BGA, but what's around it, what's connecting to. This has been our go-to image to kind of describe every single defect that can happen in a VGA. This image, I mean, if somebody actually produces this image, they're having really bad problems, right? But you can see some, like I discussed earlier, couplinarity. It means it's misaligned. There's some missing balls. There's some shapeness. There's some that because of excess solder. There's a lot of voids, splatter. There's everything. This is a perfect example of what can go wrong in a VGA. And one of the most important ones is head and pillow number 3, which is sometimes you can't detect it on a 2D inspection system. You need oblique or angle views. And what it means is that the ball essentially sits on top of the pad, but it doesn't really melt into it. It doesn't really adhere to it, kind of like your head on a pillow. So if you can see here, and the big problem with these is that sometimes they do work because they're actually touching, but then you move the device a little bit, and then it stops working. So those are the hardest one to troubleshoot. So going back to what I discussed earlier about design for inspection, what we're trying to avoid is making a system that requires complex 3D inspection. It's harder to do. It's more expensive. It takes more time, and it's very complicated. So if you design a board or some sort of device with inspection in mind, it can be a lot easier to troubleshoot and to actually analyze it. So here we're going to go over some examples of complex devices that, like in this first example, see we get a lot of capacitors on top of other devices. So capacitors tend to be very dense, so we can't see behind it. We can't analyze what's happening behind. If there's like a whole ball missing, a whole device missing behind a capacitor, you might not be able to tell. But going back, so this is what we call 2D. So same device, just by getting an oblique image or an angle view, you can start to see some of defects that were very hard to detect on the first one. You see on the bottom, there's a short right there, but because there's a capacitor on top of it, we can't see it. But by tilting or getting this angle view, you can kind of separate the two layers and getting some better views. You see there's a short on the top, there's some voiding over here. But again, this is adding a step. So what's CT? CT is what we call 3D X-ray. It can be kind of complex, but I'm gonna try to describe it as simple as I can. So let's see right here in the middle. We have our, let's say this is our PCB. So the components on the bottom are the triangles. The actual PCB is a circle, and the components at the top is a square. So as we get different images at different angles, as we're rotating, the way that they are projected on the screen changes. So if you can see number 1 at the bottom, the circle is in the middle, but we get the square on the top and the triangle at the bottom. If you go to number 5, the triangle and the square flipped. So the software starts to understand what layers on the top and what layers on the bottom, and that will allow us to separate layers and analyze layers separately. So if you see here on this example, we got a QFN on the top, which is the red, PCB is blue, and resistor is gray. So they're on top of each other in the image. But as we do a CT and we rotate the board around or the imaging around, we can actually split up, and we can see how on the top side the QFN is soldering into the board, but we can also see the bottom side, which is a resistor. So by splitting up or layering the board, we can separate the analysis and make them easier, or something that it would have been very hard with 2D or 2.5D. And here's a quick view of what the 3 different X-ray styles we have. So we have 2D, which is just top view, 2.5D, which is oblique or angle views, and then 3D, which is the actual tomography. So being able to move, rotate your sample around, slice, and manipulate it as you please. All right. So this is, it's kind of been the topic of this presentation, the design for inspection. And like I said earlier, as you go to design or as an engineer, you never design your thing to fail. But that's something to keep in mind. So keeping things away from each other, if you can move a capacitor 2 millimeters to the left or 2 millimeters up, just so it's away from another component. And those might be hard now because, you know, things are getting smaller, things are getting more complicated. But the goal is to have this as simple as an inspection tool as you can, which is a 2D inspection. It's better, and it's a lot cheaper and faster. Here are more examples. One of the things, especially in power components, you're dealing with bigger heat sinks, you're dealing with, you know, transformers, things like that, that will be very hard to penetrate. You see in the bottom, there's hardly, you know, there's no way that you can analyze those BGAs. And what companies do now, they do like sampling. So there's 100 balls in that BGA, they can test 50, and if those 50 pass, they just assume that the rest are okay. And it might be okay, but it's not the ideal route. So if you can be able to X-ray every single ball, that would be the perfect scenario. Same here, same concept here. We can see some capacitors on the left side. Well, capacitors everywhere actually. You can see right in the middle, there's a short. But is it a short or is it a component on the other side? Those are the things that are kind of confusing. And this is actually 2 BGAs on top of each other. So you can see here, there's a BGA on the left side, but there's also another one. Any sort of inspection tool is going to struggle with this, especially because the balls on one side are bigger than the other one. So, you know, we're going to rely on some visual operator inspection on these ones. And this is as simple as it gets. You know, this board is not overly populated. You know, it's not you know, this capacitor doesn't have to be here. I mean, it could be 2 millimeters to the right. It can be just somewhere else. I mean, we don't have to. This is not a very busy or populated board, so it could have been made a little bit easier, um, or inspectable. Then another BGA. You can see this one has a lot of balls in it, and they're just some resistors right in the middle. And sometimes it can be avoided. Sometimes, you know, that you have to live with it. Here again, another example. And going back again, this is just a more complex construction. This just has, I can see some transformers, I can see capacitors, I can see QFNs. This is just going to be a struggle. I mean, this is going to be a complex application, and you have to simplify. You just have to concentrate on the most important components at a time. So, you know, like in this presentation, we're looking at more voiding on QFNs, which there's a lot of voiding the QFN right in the middle. There's another one here on the right. There's a couple of big voids in there, but to automate this process, it's going to be very difficult. Again, another good image of a larger QFN. This one, like I said earlier, is just overlapping two components right on top of each other, and get complicated to analyze. Some heat sinks I described earlier with power components, like this one looks like it's some sort of computer card or something. They tend to run pretty hot, so there's a few heat sinks on it actually. There's one in the middle, and there's a little purple one. That these are aluminum. I mean, some aluminum, some they're gonna be denser, so they're gonna block your view. And you see here, because we're trying to penetrate the heatsink, we're just overpowering the rest of the board. So the rest of the board just looks white. We can't look at the image. We can't look at anything essentially. But if we remove the heatsink, we can actually see a lot more. We can actually see every single ball and analyze it. We can also see here there's some sort of like it looks like a transistor or some sort of device that has some voiding. Not a lot, but we weren't able to analyze that without removing the heatsink. So just to summarize, we are trying to avoid 3D. You know, it's essentially the concept of it. 3D is awesome, but it is a more complex design, more complex platform. So when designing components, we got to keep DFM, design for manufacturing, and design for inspection in mind. You do want to make your devices easier to manufacture, but you also want to keep them easy to inspect. There's going to be some applications that require 2.5D and 3.5 and 3D X-ray. That's just the reality of it. 2.5D is not complicated. It's just moving angles, and it's moving either the camera or the sample just to get that the side view that you want. But the way things are going, it's going to be harder and harder to keep a 2D inspection model. Things are getting very small. I mean, the Apple Watch has so much stuff inside. There'll be no way that you can inspect something like that on a 2D inspection system. Things are getting so tiny and so small, very efficient in space and real estate. So, like I said, the design for inspection, I went through that one. So, they were done. Any questions?
Yeah, we have a couple questions that came on the chat,
Okay.
and I'm glad we have a couple of minutes so you can address them. So the first question is, does the location of the void on the ball matter? If the void is in the middle, the center of the ball, on the top of the ball, on the bottom of the ball, does that matter?
Yeah. I mean, we want to detect every single void, and it's gonna, I guess it's gonna affect it differently, but our tools will just detect voids, and how the location of the void, makes your device react. It might be different, but yeah, the location will matter. But ideally, you don't want any voiding.
Yeah, and then of course you get the location in Z, right? You have to do a 2.5D or a 3D inspection
Yes.
to figure out if the void is close to the board, to the component, or right in the middle of the ball, which would be a different story. We have another question. I think we have time for another question. Is there any issues with the location of passive components? I think this question refers to the one of the slides where you showed a QFN, and the board was pretty much empty, and there was one passive component right on top of the pins,
Yeah.
basically blocking any chances of finding a short circuit between those two pins.
Yeah.
Were there any issues moving those? I guess they're
No,
asking about
I
maybe
mean, from
extra
my
impedance or.
from my uh, little, I mean, I do have some experience in PCB design. Passive components are usually filters and things like that.
Mhm,
So
mhm.
they can be moved, by all means, taking into the design in mind. So maybe moving it to the opposite side of the board doesn't make sense because you're adding traces and you're making it more complex. But things like moving a capacitor 2 millimeters to the right, it wouldn't affect it. There are some more complicated things, for communication protocols and things like that, that the trace has to be a certain length. That will be more complicated. But for
Yeah,
passive components, it wouldn't be an issue.
cool. Thanks so much, Carlos. Really appreciate your presentation. Great job again.
Well,
And for all of you guys tuning in, we have another fireside chat with the experts next week. So tune in Wednesday, 10 a.m. Pacific. And this video is going to be available online in the next couple of days. So if you know of anyone who wanted to join and missed, make sure to send them the link so they can watch this online. Thanks so much, and see you next time.
Great, which one?